All right, so we're going to kick off section 9.1, modeling with differential equations. But actually, before we do that, we're going to be talking about some terminology, some key vocab terms, definitions, before we get started, because like any discipline, we have some specialized words here that we're going to keep using over and over again, and we want to just get that out of the way, get familiarized with it. And so and if you ever get confused, right, so come back to this video and check out what these words mean. Right, so let's just get into it, right? So differential equation. So intuitively we know what a differential equation is, but what we're really talking about is it has to be an equation. So it's not an inequality, it's not an expression involving a function y equals f of x and some of its derivatives. So y prime, y double prime, whatever you want, right? So as an example here, e.g., an example of this would be something like 2x times y prime minus y equals 3. That's a differential equation, okay? It involves y prime. There's also x, right? But y is a function of x, right? Technically, this is just an ordinary differential equation, okay? So I'm going to put in parentheses ordinary. There are other things called partial differential equations. It is beyond the scope of this course to talk about them in any sense of that matter. Just know that there are other kinds of derivatives that exist that you'll cover if you go to take Math 402. But we can't begin talking about them here. So we focus just on these kinds of differential equations. Okay. Order of a differential equation refers to the highest order derivative present in that equation. So, as an example, e.g., the differential equation y double prime plus y equals cosine of x is a second order differential equation, which we're going to abbreviate as DE, okay? DE means differential equation for us, all right? A derivative that has 3 little hash marks on it in the Leibniz notation means third order. In this course, we're only going to be solving first order DEs, unfortunately. Okay, solution. You might have guessed that just like in algebra, a solution is just something that satisfies the equation, okay? But it's a function, any function that satisfies the DE. Okay, we would call that function the a solution to the differential equation. So as an example, the function y equals x squared, so standard quadratic, satisfies the DE x times y prime equals 1/2 y, okay? So just for the sake of clarity, how would we know that this is true, right? So you would have to find the corresponding y prime to put it in there. So notice that, actually, you know what, let me keep using red, sorry. Just so it's clear that this is still part of the example. So notice that y prime then is 2x, okay? And so if you replace the left side, x times y prime, don't worry about the right side of the equation, just simplify what this means. So that's going to be x times 2x Oh, whoops, sorry. See, I messed up. Wrong DE. Sorry. Okay. Then x times 2x, which is 2x squared. But x squared is y, so that's going to be 2y. Okay, now it works. Bing. Works. Whoopsie. Okay. Pretend that was right all along. So a DE may have a single solution. It may have many solutions. It's actually a very fascinating topic within differential equations that you may find a family of solutions, right? So you may have a family of solutions, and within that family of solutions, you may have a single particular solution. Okay? More on that later. The next term that we need, initial value problem. So it's a problem that we seek to solve. And so it has the form, we want to solve the differential equation that we're given, subject to, meaning we need it to satisfy another condition. And we call it an initial value problem because we typically we're looking at some initial x value that guarantees what we want. So we're given some initial point that's on the curve of the graph of the function that satisfies the DE. So as an example, EG, we may be looking at the IVP solve y double prime minus 4y equals 0, subject to y0 equals 1. So in other words, the DE here is this differential equation here, y double prime minus 4y equals 0. That's the DE. The initial value is y of 0 equals 1. So the point 0, comma 1 is a point on that particular solution. An IVP always gives you a particular solution. Okay? So there's that word again. Another kind of problem that we might have is what we call a boundary value problem. Boundary value problems in this context are actually not too complicated, but we may end up, if you take a higher math class that begins to talk about partial differential equations, this actually gets very complicated very quickly. So the form here is still, we're going to solve some DE, but this time what we're subject to is at least two conditions. Actually, always a even number of conditions. So y of A equals y1, and y of B equals y2. And what you want to think about here is basically what we're saying is we're looking for the solution to a DE over an interval a comma b, right? And at the endpoints of the interval, the boundaries, we specify two specific y values, okay? And so roughly what we want to think here in terms of initial value problems and boundary value problems, which we call IVPs and BVPs, okay? An initial value problem typically is going to give you, we want some curve that passes through a specific point initially, okay? So this is your particular solution to an IVP. A BVP, on the other hand, is going to give you a particular solution that's bounded to two endpoints. Okay, so That's really the difference there. But we're just going to be giving these. We're not going to think about them too deeply. Next, the last thing that we want to talk about here is you're going to hear the term linear, okay? And there are other subtypes of differential equations, but for now, we're just going to leave it at that. And a linear differential equation has all derivatives and y are in a what we call linear combination. Again, something that you'll look ahead to that in Math 410, linear algebra, and it'll make more sense then. But really what we're saying here is a linear combination then is you have real number coefficients to your terms involving y prime and y double prime and y triple prime, whatever derivatives you have, and there's no exponent on the derivatives or y, and there's no trace of x. Okay, x could be in the other side of the equation, but not with these terms. Okay, so this is a linear third order differential equation. Okay, all right, and now beyond that, there's a wide variety of much more specialized language that we would need if we wanted to delve more into this. We're going to leave it at that, but just remember that these are the terms that we're going to be using for the most part when we are working through these sections, and then we're going to develop some more exciting ideas later on.